Hello everyone. Can you hear me? Can you guys hear me?
Yes, sir.
Um, so this is a live interaction section. So you guys feel free to switch on your camera and switch on your microphone, and you can ask me questions any during the sessions. So this would be the interaction session for Foundations of Computational Fluid Dynamics, uh, uh, offered by IIT Madras by Professor Venkatesan. I will be the tutor for this course. I will be hosting all the live interactive sessions uh, in this time. So this would be the first class. Um, I think you guys would have yeah. So I think you guys would have gone through the first week's lectures, I guess. So if you've gone through the first week lectures, it's going to be it is a basic lecture, basic lectures, basic fluid dynamics equations. So we didn't enter into computational fluid dynamics or CFD, whatever we are going to teach. So um, and you might also gone through the weekly assignments, practice assignments, everything. So all those are basics and straightforward questions. So if you have any questions regarding that, you can ask me. So first of all, let me introduce myself. I am Ganesh Kumar. I'm a student at IIT Gandhinagar. So I will be the TA for this TA tutor for this course. All right, so let's get started. You guys can stop me at any time and you can ask me questions. So
Okay, sir.
this week, uh, interaction sessions, what we are going to do is we will first computational fluid dynamics. What is the need for doing computational fluid dynamics? So to know that, we need to excuse me for a second. Yeah, sorry about that. So I'm just checking my recordings. Okay.
Sir, excuse me, sir. Uh, Sir, can we get this recording after this session, sir?
Yeah, yeah,
In
yeah. Yeah, it will be
our,
up.
sir.
Right. So it will be uploaded in the YouTube, and you will get the
Okay,
YouTube link either
okay,
through
sir.
email or in your NPTEL dashboard. So you
Okay,
can
sir. Okay.
always go and check, rewind it back, and you can check it again. So
Yes, sir. Yes, thank you.
yeah. So let's get started for today's sessions. So as I said before, we will understand why we need to do computational fluid dynamics. Uh, so the reason for us to do computational fluid dynamics or any solving any fluid problem through a numerical method is we cannot solve it analytically. So the so why we can't solve it analytically? What are the challenges we face when we solve it analytically? That we will look into this session. Um, so I will take a very basic problem, fluid flow problem, uh, which is a flow between parallel plates. You guys must have already known this problem, um, but still I would like to state. So still I would like to state each and every assumptions and show you the difficulties in solving a Navier-Stokes equation for even a simple problem. So let's get started. This is going to be a flow between parallel plates. So as you can see, um, stop me at any time and you can ask me questions. So until unless there are no questions, I will move forward. Uh, so let's get started. So as the name suggests, there's going to be a flow between these two parallel plates, this plate and this plate. And the flow is going to be um, by the pressure gradient. So there's a pressure gradient direction, and the pressure gradient is going to drive the flow between these two parallel plates. So we will take the choice of coordinate system is ours. We will take the coordinate system like this, the center of the pipe, um, and the plates are spaced at with a distance of h from the center. Um, so to solve any fluid problem, first of all, like what we are going to solve, what we need to know in this problem. So do you guys have any idea what we need to solve for? You can unmute yourself or you can type in chat box. Anything is fine. Right. So we got an answer, Abhishek, telling we need to solve for pressure and velocity. So that is true, pressure and velocity. But the problem in solving these two is the velocity. Let's say let's consider only two directions here, x and y direction. Let's ignore z direction, or let's say we need uh, it's very wide a channel, let's say. Let's ignore the z direction. Along z direction there's no way. So to solve pressure and velocity, we know that velocity is a function of x, y, and then t. So actually it should be a function of z direction too, but we are ignoring z right now. So it will be a function of x, y, and t. It is not a simple function like x square, y square, x like u is equal to some x square or some constant times x plus constant. It's not such simple. Similarly, there is going to be a y velocity v. V is also going to be a function of x, y, and t. And similarly, there's a pressure. Pressure can also be a function of x, y, and t. So if we look at these these three parameters like two velocities and pressure, all are function of x, y, and t. So solving this complex system is going to be problematic. So if you want to solve, let's say we are determined to solve this. So what are the equations we need to follow? So what are the equations this flow should satisfy? Do you guys have any? So what else? Right. So conservation of mass is continuity, and then momentum. Right. So is there any other equations you need to solve? So yeah. Um, So since we will make an assumption like it is an incompressible flow. So for an incompressible flow, we no need to solve a energy equation. Actually, the conservation principles are for mass, momentum, and then energy. So we need to conserve mass, momentum, and energy in any flow problem. So in an incompressible flow, we no need to care about energy because the temperature is not going to depend on your flow velocity or the pressure. But if you are going to compressible flows or high speed flows like a CD nozzle flow, a rocket flow around a airfoil, so there the temperature is going to be dependent on all lot of lot of uh, like parameters. So at that time you need to solve energy equation also together with continuity and momentum. So let's first look at what is the continuity equation. So since we are dealing with incompressible, the equation one is going to be our continuity equation. Uh, you guys also might know another version of continuity equation, which is just del dot v is equal to 0. So what this continuity equation basically tells, like um, so this So it actually conserves the mass. So if you take any control volume, um, I recommend you guys to go and look at how it is derived. So it will help you understand better. So what a continuity equation is. So if you take a control volume, let's say this is a cube or control volume, any control volume, whatever comes in goes out. So the balance between these masses, uh, basically. So here we wrote a different uh, uh, like modulation of continuity equation. It's in a vector form of this equation. So these two equations are for incompressible flows only. So uh, uh, when I say incompressible, what I say is the total deformation of any control volume is going to be zero. So if this is cube, if this cube deforms, or let's say if this cube of mass fluid is flowing, if it deforms, the total volume will remain same. The total strain rate will be same. So that's what in incompressible flow the continuity equation means. Or you can simply say we are going to conserve the mass. So this is the continuity equation we have, and the momentum equation. So we have two directions, x and y. So there's going to be two momentum equations. So this momentum equation basically comes from this actually called as Navier-Stokes equation. So for any flow problem, you need to solve continuity equation and Navier-Stokes equation, which is a momentum equation, and there will be energy equation based on whether the flow is incompressible or compressible, or in some special cases you need to solve energy equation also. So so from where this Navier-Stokes equation comes, so if we look at this part closely, so this part is actually density times kind of acceleration. If you look at dou u by dou t, velocity, the time derivative of velocity, it's a kind of acceleration terms. So density is kind of mass term. So if we look at, if this part of the equation is actually ma, mass times acceleration, and the other three terms is actually the pressure is what driving the force. So the this is actually a force. So this is a pressure force, and see, you can see a viscosity, mu is a viscosity. So this is a viscous force, and this is a body force. If you have any body force like magnetic force, gravity, so if you have such kind of force along the x direction, so you need to add these force. So finally it turns out to be F is equal to ma, which is a Newton's second law. So momentum is basically Newton's second law. F is equal to ma. So what is the difference between that equation and the momentum equation? So the momentum equation, the Navier-Stokes equation, is written for a control volume, but F is equal to ma is written for a mass, a fixed mass. We call it a system, control system kind of thing. So if you write a momentum equation for a fixed mass, it will be Newton's second law. So, but we are writing a momentum equation of fixed volume, a control volume. Control volume is the volume which we are interested to study. So there, the uh, the Newton's second law will be recasted or casted in a different form, like a Navier-Stokes equation, which is a momentum equation. So we need to write two momentum equation in both the direction, x momentum and y momentum. So if we look at the momentum equations also, this dou u by dou t is a temporal derivative, and these are convective derivative. So these all corresponds to the acceleration of a fluid element. So this is mass times acceleration times the force acting on the control volume. So we see there is a pressure gradient, and there is a viscous force, and there is a body force. Similarly, similar thing goes for y momentum equation. Uh, what are the forces acting? So it's actually Fx equal to max, and Fy is equal to may. So this is exactly we are going to solve. So for any, that's the beauty of this CFD, like not fluid dynamics. Like in any problem, if you take, there's going to be mass conservation and momentum conservation and energy conservation. So if you are going dealing with particle dynamics, or if you are going to dynamics of moving bodies. There also you are going to solve the same equation like Newton's second law. So in fluid mechanics, we are solving a different equation where actually it is derived from Newton's second law. So I recommend you guys to go and look into the derivation of each and every equations. It will be in all standard textbooks. So how we got, why we got these four terms for acceleration. It's going to be one acceleration, but why we got four terms in acceleration. Similarly, viscous force, how it turns out to be like this. So everything I recommend you guys to go and look into the derivation. So it will help you understand better. If you find any difficulties, you can come back and ask me in the next session. So, so coming back to the discussion, so let's say this is our problem, flow between parallel plates, and for this problem, if we want to solve the meaning, so what I mean by solving is solving for velocity and pressure. So, so to solve for velocity and pressure, we need to have continuity and momentum equations. So we will solve for continuity and momentum equations. One important thing is, so now if you see, we have unknowns, three unknowns actually. So we have U, V and pressure. And we also have three equations. So basically for any mathematical system of equations, if you want to solve it, then the number of equations and number of unknowns should be same. And here we are going to have three equations and three unknowns, which means you can solve it. But it doesn't end there. There are a lot of difficulties comes. So for example, if you look at here, we have three unknowns where each unknown is velocity and pressure, and we have three equations. Now, but the pressure term is present in only two equations. It is not present in the continuity equations, which is one of the difficulty. And and we have simple differential equations, like we don't have any uh, ordinary differential equations. We have partial differential equation, and solving partial differential equation requires some techniques to be followed when you solve it analytically. So here we have, like if you see, we have each variable is going to be function of three different parameters like x, y and t. So in order to, if you want to solve this set of equations, it's not at all, it's not possible. It's still under research. There is a millennium prize also for this. If you are able to solve these three equations, you'll be given $1 million by I'm not sure, some mathematical institute, I guess. So so solving this equation is going to be very difficult. The reason for me to say is, if we look at these terms, the convective terms, all these terms, here velocity is unknown and there is a derivative of velocity multiplied to it. It is actually a non-linear term. These three terms. So when I say non-linear, it's like if the two unknowns are multiplied, or if it is u square, v square, then these terms are kind of non-linear terms. And you can also go back and check what non-linearity means. So like let's say, for example, if I state what I mean by non-linear, so non-linear means, let's say you have two functions f1 and then f2. So f1 of x and f2 of x. Okay. So now if I have another function f3, or let's say, let me go back. Say I have let's say two variables, like I said x and y. Okay. So now I have another function phi, which is actually x plus y. Now I can write phi of, it's actually phi of xy. Phi of xy is x plus y. This I call it as a linear function, because if you add these two, let's say I am having a phi 1 which has x1 and y1, I can have x1 plus y1. And similarly, if I have another y2, which is actually x2 and y2, which is a function of x2 and y2. So x and y, let's say you consider it as a coordinates, like x and y are coordinates, and phi is a function which is a function of a coordinates x and y. And that function is defined as x plus y. So for one point it's x1 phi 1, and for the second point it's x2 1 y2. So when I say linear, I can write phi 1 plus phi 2 equal to which would be x1 plus, I go back one second. So if I write another function, let's say phi 3, which is a function of phi 1 plus phi 2, okay, so I can simply write, so this can be, this will be x1 plus x2 plus y1 plus y2. Similarly, I can also define a variable x3 and y3, which is actually x1 plus x2 and y1 plus y2. So when I write phi 3 as a function of x3 and y3, I'm basically, so it actually scales linearly. The similar thing won't go if the 5 is like, let's say, x square plus y square. So you can't write a third variable like phi 3, which is a function of x3 and y3, which will be x3 square plus y3 square. This you can't write it as x1 square plus y1 square, so x1 plus x2 square plus y1 square plus y2 square. So this you can't write it. This linear scaling you can't write it because it's a square term is there. It's which is a non-linearity. So you can go back and look at non-linearity. So it's just I'm giving only one example for non-linearity. There is one more condition which I'm not giving. Leaving it as an exercise. So the linear scaling is not available. So similar thing goes here. So here u is a function of x, y and z, and v is also a function of x, y and z. So it is actually a non-linear term. If the two parameters are multiplied, are to put it very crudely or simply, if two dependent parameters are multiplied together, then it becomes a non-linearity. So these three are non-linear terms. Solving it is very difficult. So we don't have analytically you can't solve it. So for that, if we need to solve these three equations, you need to make few assumptions. Let's make some assumptions in order for us to solve something and get some answers. Okay. Um, so let's say one assumptions we already took, which is incompressible. We wrote for only uh, wrote incompressible continuity equations and Navier-Stokes equation. The Navier-Stokes equation, this is also for incompressible equation. For compressible equation, the rho will be multiplied inside. It won't be separated out. So this one incompressible assumptions we already made. The one more assumptions we are going to make, it is going to be very large and wide channel. Okay. So when I say very large and wide channel, there is not going to be any variation or velocity along y direction and z direction. So I will tell that this is one of the simplifications I am making. Like let's say the channel is very large and wide. So along uh, w direction there is not going to be any, along z direction there is not going to be any change in velocities, and here velocity along y direction is also I am making it 0 because the length of the channel is very large, so there is no going to be any velocity profile. And we can also see that the channel is bounded by two fixed plates, so the fluid is not going to cross those plates. So that is one thing. So we are going to assume that v and w is 0. So when we assume that, the equations simplifies. So how it is going to simplify? Let's copy this again. Um, by the way, do you guys have any doubts? You can stop me anytime and ask. So here for continuity equation I'm making v and w 0. So what happens, this dou v by dou y would be 0, dou w by dou z would be 0. And similarly in x momentum equation, v is going to be 0, so this term goes to 0. W is 0, so this term also goes to 0. And what else can be 0? Yeah, y momentum equation. So in y momentum equation, can anyone say what are the terms would go to 0? Like I'm just making v to be 0. So terms would be 0. Yeah, right. But this term would be 0 because velocity is 0, v is 0, v is 0. This term also would be 0. That is true. Here also this term would be 0, this term would be 0, this term would be 0. We didn't say. So one thing we didn't say is now we will consider the body force to be 0, but this term is not yet 0. The pressure, this term doesn't go to 0, but due to the, yeah, body force will be there, true, but I'm assuming there's no body force. So that is one of the assumptions. Let's make that assumptions too. So is it clear? Like I'm making body force also to be 0. So the important, uh, so after making all these assumptions, so after making all these assumptions, you can see that the continuity equation becomes dou u by dou x equal to 0, which is better. We have simplified it just by making one assumptions. And the x momentum equation becomes rho times dou u by dou t plus equal to minus dou p by dou x plus mu times the whole term would be there, which we will write. I will simplify, I will write it like this, plus I'm making the body force to be 0 again, so this would be 0. Okay, so so what is the other equation? The other equation would be minus dou p by dou y is equal to 0. So from these three equations, can you make some conclusions? What are the conclusions you can make? So let's say the first equation. First equation which tells that dou u by dou y is 0, which means that of x. So if u doesn't depend on x, then derivative of that is going to be 0. That is one thing. And this equation tells p is not a function of y. So we have greatly reduced the uh, some complications, like, so before u is a function of x, y and t, now u is going to be function of only y and t. And similarly pressure is going to be function of only x and t. So and v is of course we made it to be 0. So is this clear, like why I made u as a function of y and t and pressure as a function of x and t? So I'm going ahead. So Uh, there-
This one I'm asking user function of y comma t. So can you explain this again?
Sorry, I cannot able to hear you. There are a lot of background noises. Can you tell
So
again?
sir, sir, how u is equal to function of y and t. So
So,
can you understand?
so how u is equal to function of y and t? Is that your question?
Yes, sir.
Yeah. So we first started with. If we go back, we first started with u as a function of x, y, and t. Okay. So now we made an assumption. We made an assumption that v and w is 0, right? So if v and w is 0, this term is going to be 0, this term is going to be 0. So what remains is dou u by dou x is equal to 0. Is this clear?
Yes, sir.
So if dou u by dou x is 0, if dou u by dou x is 0, u cannot be a function of x, right? So if u is a function of x, the derivative of that will be equal to something, let's say some constant or something, it will be there. Like since derivative is 0, then u cannot be a function of x, right? Is that clear?
Yes, sir.
So if u is not a function of x, you can eliminate that term. So it will be become a function of only y and t.
Understood, sir.
Okay. So similar thing goes with pressure also. Pressure, the y momentum gave us dou p by dou y is 0. So so this sorry. So this so p again cannot be a function of y. It can be a function of x and t only. So is this clear? So
Yes.
yeah. So I will go ahead. Um, uh, One more assumptions. So again, if we look at this, yeah, one more thing you can do here. Um, we can still write since u is not a function of x, or yeah, since u is not a function of x, this dou u by dou x is also going to be 0. So dou u by dou x, this term also goes away. So now the remaining equation will be like this. So we have so remaining equation after simplification we can simply write rho times dou u by dou t, which is equal to minus dou p by dou x plus mu times dou square u by dou x square. I wrote it simply there, like I will write it again. Dou x square, dou square u by dou z square. Since we already assumed dou u by dou x is 0, this term would go to 0. Again, u is not a function of z because we don't have z velocity or z direction things. We are completely ignoring. So this term also going to be 0. So the final resulting equation would be rho times dou u by dou t is equal to minus dou p by dou x plus mu times dou square u by dou y square, right? This is the equation we have. Now we see that still it's in the second order partial differential equations. So if you have gone through the lectures, you know the classification of PDEs, right? So we can write it in terms of discriminant. It's discriminant, which is actually b square minus 4ac. So so can you classify this PDE? So what kind of this is of course a PDE because there's a partial derivative term. So can you guys guess like what PDE it could be? Elliptical, hyperbolic, or parabolic? So you guys gone through the lectures, right? So for equation to be hyperbola, what will happen? The discriminant, let's say that is delta, which is actually b square minus 4ac. This should be so if we look at this equation, if we write, so u is a function of y and t, right? So if we look at this equation, if we write in a very generalized form, first let's say a times dou square u by dou y square plus b times dou t plus c times dou square u by dou t square plus e times dou u by dou t plus f times dou u by plus g is equal to 0. This is more generalized form of writing a partial differential equations. So if you compare these two equations, what happens? This e term is there, this term is not there. So one second. So this term is not there, right? So this term won't be there, which means that c is equal to 0. Um, so c is actually equal to 0 because second derivative of t is not there. We have only one single derivative of t. So e is there, but e is actually coefficient of dou u by dou t, which is actually rho. E is there, but c is not there. Okay, so if we strike it out, this term goes away. So dou u by dou y is also not there. This term also goes away. This term goes away. This is going to be rho. B, we don't have b, so again b is equal to 0. And a, how about a? A is going to be mu. So is this clear? Yeah. So if we look at this, if we write b square minus 4ac, let's say, so what happens? B square would be 0, the discriminant would be 0 minus 4 times a would be mu, c is again 0 because second derivative of time is not there. So this term turns out to be 0. So it is not clearly greater than 0, right? It is actually, what kind of equation is this? So yeah, this is para. So again solving, yeah, are the recordings also. You no need to worry. But if you have doubts, you can ask me now also because that's the meaning of interactive session. So anyway, so this clearly tells that it is a parabolic equation. Solving a parabolic equation of this type is also going to be very difficult. So if I want to give you some techniques which you can use it to solve this equation. So if you want to see some techniques, let's say you can check this techniques later. Like there are some techniques like method of separation of variables and method you can use it to solve this equation and some series solutions. These things you can check. Okay, so these are little advanced PD methods to solve any equation. So this you can check and you can solve it if you want. But still with the present knowledge of PDE, it is very difficult for us to solve it. So let's go ahead and make some more assumptions. Okay. So one more assumptions would be, what assumptions can we make? So let's make it more simple. So do you guys have any suggestions for assumptions to make? What assumptions can we make? One assumptions we can make is,
Viscous free.
yeah, viscous free you can make, but I will tell you something. Uh, the problem statement. So if you remove the viscosity term, there is, so what viscous actually means? There is a, if there is a friction between the fluid elements is what is uh,
Yeah, between the fluid layers.
uh, so if your viscosity is zero, or if you are making viscous free, what happens? The velocity at the wall here, it won't be zero, but so you can't make that assumption. So the assumptions you make should be meaningful when you make an assumption. So what you can do is, you cannot make it viscous free over here. Only in the some high speed flows you can make viscous free assumption. That's because the viscous term is actually dominated by the inertia term. So if we look at this equation again, x momentum, so this is an inertia term, right? MA, this is an inertia term, and this term is viscous term. So at high Reynolds number, what happens? The viscous term will be the viscous term would be very less, so we can ignore it. So always you will ignore the viscous term but not neglect it. So you can't neglect that one. Okay, is that
Yes,
clear,
sir.
Divam?
Yes, sir. Very much. Thank you.
So as Uzair said, we can make steady state or steady state assumptions, which means like at time t equal to infinity, like let's say time t tends to infinity, like the fluid, all the transient things settles down. Okay, so when you make that assumptions, what happens? The actually what this means is, this assumption you can safely ignore dou by dou t of any terms is equal to 0. So when you make this assumption, the so first we had three equations. We made one assumption. We reduced and those gave us three simplified equation, and those three simplified equation can be substituted with each other, and we got some uh, comparatively simplified equation like this. Now when you make steady state assumption, what happens? This whole term goes to 0. So when you make that assumption, the equation becomes minus dou p by dou x is equal to actually plus is equal to mu times dou square u by dou y square. So I took a pressure gradient this side. So I took a pressure gradient this side. So when you take it this side, becomes positive. So mu times dou square u by dou y square. So here it is still a partial derivative. Wow. So yeah, is it still a partial derivative? What do you guys think?
Yes, sir. Of course.
So now, yeah, thank you for the response. So if we look at here, we made it steady state. Okay, so our solution doesn't depend on time now. So if it doesn't depend on time, this term is, we are going to neglect it. So what this tells, um, use a function of y only finally, and p is a function of x only. So this is the final conclusion we are going to make. Like a function of y only and p is a function of x only, because at steady state, uh, uh, for the yes, 12 AV. I saw you have raised your hand. 12 AV. Sorry, I don't know his name. 12 AV. Some issues with microphone letting. So if we see here, not going to depend on time. So our solution will also is not going to have time dependency. So u will be a function of y only and p is a function of x only. But now another important thing to note here is, so dou p by dou x is a function of x. Okay, it's a function of y. Can these two be equal? What do you guys think? Can these two be equal? If it's not equal, did we make any mistakes?
Because of assumptions, actually, it's becoming an equal, but generally it is not equal.
Right.
Am I right, sir?
Right. So, because of assumptions, you are telling it is equal.
Yeah.
But a function of x and a function of y cannot be equal, right? So, if it wants to be equal, yeah, you whatever you said is true. Because of assumptions, it comes out to be equal. But if the both the functions are same, what it means? Like, is it what kind of function it can? What geometric function? What kind of function it could be? So you are telling this is a function of x and this is a function of y. X and y are two independent variables. X doesn't depend on y doesn't depend on x. But
Yes.
the function is coming to be same. So when this is possible? So do you want to try? Want to guess? Not, I will tell you the answer. If a function of y and function of x need to be same, these both be a constant. Let's say dou p by dou x is some constant. And similarly, dou square u by dou y square times mu is a constant. Those two constants would be same. So constant can also be regarded as a function, but it doesn't depend on any dependent variable. So if function of x and function of y have to be same, then those two should be equal to a constant. It cannot be a quadratic function or trigonometric function or hyperbolic function or anything like that. So what this clearly tells is our equation becomes more simplified. We can write it as an ordinary differential equation. It's going to be dp by dx, which is equal to mu times d square u by dy square, and it is going to be a constant. It is equal to some constant. We don't know that constant yet. Okay, is this
Yes, sir.
okay? So if this is clear, uh, what this essentially tells is, by it's actually constant. The pressure gradient we apply is no more a function of x, it is a constant. So P is not a constant, but pressure gradient is a constant. Sorry about that. So which means that you can write it like one second. Dou P by dou x equal to some g, let's say, some constant. You can write it like a constant. The pressure gradient is going to be constant. So which tells that, like, if you have a thing we are solving for, so this is terminal 1 and this is terminal 2, let's say. Here we have P1, here we have P2. So pressure gradient is simply 2 minus P1 divided by this length. So pressure doesn't vary, which essentially tells pressure doesn't vary. I mean, along x it will vary, but the pressure gradient remain constant. So that is what it tells. So if it is a constant, let's say, then more easy to solve, right? Like you have mu d square u by dy square, which is a ordinary differential equation, which is some g. Okay, g is dp by dx. Let's write it here. Uh, we can write it ordinary differential term, so dp by dx. So now you guys are good at solving this differential equation. It is going to be g by mu. It is a simple second order differential equation. Now, is this clear till here?
Yes, sir.
So what would be the next step? You just need to integrate it once. So it will be g y by mu plus c1, right? Some integration constant, and u will be again g square by 2 mu plus c1y plus c2. So finally, velocity profile. It is actually a function of y. Is this integration clear? Like you guys should be very good at integration by now.
Yes, sir.
Yeah. Uh, so here still our job is not yet over. We still need to find C1 and C2. Like how do we find C1 and C2? Any idea?
By using boundary conditions.
Right. So what are the boundary conditions you will take? Let's go back at
Initial
the.
velocity.
So right. I will tell you why initial velocity is not a correct boundary condition. So
Yeah, yeah.
initial velocity is at time t equal to 0, right? So we are not solving from time t equal to 0. We has reached steady state, right? So we are not solving temporal variation. So it's it you can't give time t equal to 0 actually. And one more thing, that is an initial condition. It is not a boundary condition. Initial condition, the difference between initial and boundary condition is initial condition can be specified at only one time or at one specific parameters value. So let's say at time t equal to 0, what is the condition you are giving? That is going to be a initial condition between two boundaries. Like for example, if you take here, the boundary condition would be, what you can do is at y is equal to minus h, what you can, velocity is 0, u velocity is 0, because it is at the contact of the plate, and since plate is fixed, the fluid also will be fixed over there. So you can take one condition, and another boundary would be here at y equal to plus h. At both these places u is 0. Okay, so boundary conditions are specified at 2 points. It's not specified at one single point, but initial condition is specified at one. Please note that. So is this clear?
Yes, sir. I have asked.
Okay.
Sir, I got one other doubt also. If it possible, at the end of this lecture, can you explain the physical meaning of elliptical parabola and hyperbolic with respect to CFD?
Sure.
Cause actually in the video in the Sar actually explained, but that was I was unable to understand that. So
Right.
that physical meaning.
Right. Sure. Let me finish this. We have 3 more minutes. Before that, let me finish. Uh, so the boundary conditions would be, um, at y is equal to minus h, u would be 0, and at y is equal to plus h, again 0, because of no slip. So we say it is a no slip boundary condition. Okay, there is not going to be any slip between the plates and this thing. So now you can apply this boundary condition, you can and get the velocity profile. This is one set of boundary condition, or you can apply another set of boundary condition. So let's take it, this is BC1. this is BC2. You can apply either of this. You will achieve the same result. You can you take it as a homework and do it. So at y is equal to h, u is equal to 0 plus h. That is comes from no slip. One more boundary condition called symmetric boundary condition. Y is equal to, at y equal to 0, which is at the center, the dou u by dou y would be, would it be, can you guys guess?
Zero.
Right. So why I said 0 is there's going to be, so this is called symmetric boundary condition. So the profile, the velocity profile at finally you will get, let me state the final velocity profile. So this I will leave it to you guys as a homework. You can do it. If you find difficulty, you can come and ask me again tomorrow. I mean, next session. So it would be 2 mu dp by dx, which is actually g h square minus y square. So based on time availability, to, I'm giving the final thing. So if you look at this boundary, dou u by dou y, it is actually a Neumann boundary condition. If you have gone through the lecture, there are different kind of boundary conditions. Professor will explain. So these two boundary condition is actually a Dirichlet boundary condition, where you are specifying the value. This is the value, specifying the value of dependent parameter at the some location. Then it is a Dirichlet boundary condition. If you are specifying a
Sir,
derivative, yeah, yeah,
sorry to interrupt, sir. In the second boundary condition, that comes under mixed boundary conditions things now, sir. One is Dirichlet and second one is Neumann and the third one is mixed boundary conditions, no? So the second, yes, sir.
right. So when I say Neumann, I'm talking about only this. So what you said is true. As a set, it's a mixed boundary condition. Why I say mixed is it has a Dirichlet and it has a Neumann as a set. But if you consider only this condition, it is a Neumann kind of boundary condition. This is a Dirichlet boundary condition. That's what I'm trying to say. So as a whole, it is mixed. You are right, true. But only this is going to be Neumann condition. It's called Neumann condition. We specify that zero gradient is there. So when you solve for a problem, you can just simply ignore the other half, and you can solve the from the center line to the upper plate, or from the center line to the lower plate. You can solve for it, and again you will reach the same solution. You should get the same solution. So, so is it clear, Divakar?
Yes, sir, very much.
Yeah. So, um, what we understood from this solution procedure is that we have to make lot of assumptions to arrive at a simple solution. So, if you go back to our problem statement, can you guys think of any place where this kind of problem is there? Like, is there any two parallel plates where there is a flow is in between? So you may not come up with any application because this kind of this is a
Electronics cooling actually it will come now, sir. Between two,
yeah true
yeah, may
yeah
not be
between two
proper.
fins between two fins
Yes, sir. Fins.
but it's a very large and very wide. We don't have very large and very wide in a electronic application. Do we have
The water canal.
water canal? Right. So in water canal, true, water canal is there, but is it a free surface flow? Right. It doesn't.
Yeah, yeah. Yeah, we generally in our villages, water canals will be there. No, in that manner I'm not talking.
Okay, but it is not bounded by the upper plate, right? It is bounded by lower plate, and it also has lot of complexities in it. So this is a more ideal case. You cooling you can do in water canals too if it is bounded by two plates, and you can very ideal situation. Uh, it a steady state, unsteady. If you want to know how the flow evolves, then you need to solve using lot of this method of separation or all these things. You need to solve it based on these analytical procedures. And again, if we consider the boundedness of the channel, let's say, as you said, channel width and height would be given. Similarly, length also would be given. We can't have an infinite length panel channel. So, if you consider all these things, what happens? The applicability of this solution is no longer there. So, we need to solve this whole set of equations. So, whatever we did till now, the applicability is very less. You can't apply it to a normal um, uh, any normal situation. So, to have a better applicability to solve any real problems, we need to solve this whole set of equations, which is not possible through analytical. Whatever we did now, it's not possible through analytical. The only way to do is to have some approximation, to do some numerical methods. So which you will learn in upcoming classes. What are the numerical methods, the finite difference schemes, finite volume schemes, and there is finite element, which is more active nowadays because a lot of people are doing finite element also with CFD. So, but CFD is mostly of with finite volume techniques only. So, we will somehow construct this set of you see 1, 2, and 3. 3 non-linear partial differential equations, coupled partial differential equations. If you say these three, it's system. The system is 3 non-linear coupled partial differential equation. All sorts of complexities are there. So to solve it analytically, it's not at all possible. That's why we need to handle it carefully using a numerical method. For even for a complex partial differential equations like this. So that's what you will see in this course. At the end of solve this full Navier-Stokes equation using a numerical method. You can use CFD software, but you may not know the. But if you write your own code, you will understand what exactly the CFD is. So at the end, finally, you are going to solve this and this equation, these three equations only for any incompressible flow. But you will take care of hyperbolic, parabolic, or whatever the nature of the equation depends on that. You will be able to construct a schemes, finite volume schemes, and you will be able to solve for any real value problems like channel flow, as which you where you no need to do any assumptions like this, like a steady state or incompressible, like very large and wide, no body force. If you add body force, again the complexity will try it, like adding a body force, and again you can try solving it. You might end up getting so body force would be a constant. You might end up getting solution. You can try it. So that's the motivation of doing a CFD. It's really using to exactly capture the fluid flow problems. So by this note, I will you guys, if you have any doubts, you can stay back and ask me, or you can leave. We will meet in next session with more discretization schemes. So I think next week you guys will be introduced to discretization schemes, how to approximate a derivative. Um, we will. Thank you.
Thank you, sir.